a little bit of our research and some other just hopefully practical tips to help with water management in macadamia orchards. So trying to make it fairly practical, and some really good advice and just explaining perhaps how to make the most of every drop in an orchard, bearing in mind that it really isn't the simplest thing in the world to get right, and it's quite complicated. So today, let me just find my mouse. What we want to do, what we will be talking about is just, first of all, just to put everything into context. So why should we worry about water? Why is water so important? And then after that, we'll just have a look at the orchard water balance. So if I apply water to my orchard, or if it rains, where does all that water go? It's really important to understand that if you're going to minimize losses and maximize what you really want to happen. And then we'll have a look at what factors drive water use. So how does a whole lot of factors impact the evapotranspiration from your orchard? So how much water is lost from the orchard? And then we're going to look at, well, what information do I really need to make good irrigation decisions, and where can I get that information from? And then we'll have a look at how do we determine orchard water use or evapotranspiration, and we'll look at one of the most popular approaches, the crop coefficient approach. We'll try and explain it a bit. So once you know how much to apply, how much to irrigate, how do we assess irrigation practices? So Stefan Skuman has given me a really, really nice analogy. It's the rudder that steers the ship. So how do we make fine adjustments by assessing what we've done? So retrospectively looking at, is what we saw, what we expected to happen. And then Seneleko is going to tell you a lot about his PhD research, what happens when there's not enough water. It's a scenario that might become increasingly important. So he will have a look at ways to schedule when perhaps there's not enough water available. And then at the end, we're just going to give you some take-home messages. And hopefully those are the things that stick. And if you come out of today with one or two things that have just, really made sense and will help you, then, man, we are doing, we'd be super chuffed. Yeah, and it's really nice to work with the guys from SAMAC. So Lisa and Alria always give us such magnificent support. So it's also a privilege for us to work in the industry. Okay, so let's start with why is water management so important? So on the left-hand side, it's barley, but the same principles apply to any crop. So transpiration is correlated with dry matter production. And you can see there that the yield of dry matter and the number of barley varieties increased as transpiration increased. So there's a direct relationship. And the reason for that direct relationship is that if stomata stay open, photosynthesis increases. So that's the image on the right, and that is data from macadamia. And so keeping stomata open will equate to more photosynthesis. As we all know, if the soil starts drying out, then stomata start to close, and that compromises photosynthesis and dry matter production. So I want to put water down, and I want to use water. I want the plant to use water because that means I can get increased dry matter production. Doesn't always mean increased yield, but without photosynthesis, I can't get increased yield. And what's really important in South Africa is the question, will we always have enough water, and what does the future look like? And so Alria was at Agri-SA conference this morning, and she gave me some predictions from Francois Engelbrecht. So SA, as we all know, is a climate change hotspot. So things are going to change in South Africa, and they are changing. Generally, springs are going to be drier, which is what we are experiencing in the last 2 seasons. It takes a while for rain to start. So later onset of summer rains, and then we have more intense rainfall and flooding in the eastern regions of the country, where a lot of macadamia production is taking place. Then intense rainfall means that a lot of that rainfall that we receive will no longer be effective for production. So you'll get a lot more runoff and a lot more deep percolation in your orchards as a result of very intense rainfall events, which also has consequences for things like erosion. And so in general, effective rainfall is likely to decline. The other major concern for us is potential changes in water allocations in future. So government might decide that they want to change water allocations to agriculture. At the moment, agriculture receives the lion's share of water allocations in the country, and probably for really good reasons. But there's so much competition from a growing population and industry. And where do you get that extra water from for a growing population? Well, agriculture is seen as a potential source. And so we're not sure what those changes are going to be in future, but we need to be ready for them. And so it's not going to be business as usual in future. And we need to make sure that we use water much more sustainably. The other big question that we hear all the time is what about quality of water? So it's not just the amount of water, but what about the quality? And so people are really worried about biologicals in water, so human diseases that are occurring, like E. coli, just one of them, it's in water. And the other issue as well is increased salts and other kinds of pollutants. If you look at the Vaal River, it's got worrying amounts of salt and biologicals in it. And how do we deal with that change in quality of our water as well? So onto the orchard water balance, and where does all this water go when I apply it? And it's really important to understand this if you're going to maximize one component, which is transpiration. So if we have a look at the orchard water balance equation, that delta SWC is the change in soil water storage or soil water content. And that is balanced by the gains, things that I add to the system, and losses, things that are lost from the system. So the gains is basically my irrigation and my precipitation, and how do I make the most of those, and how do I know, how much has actually been applied to change soil water storage. And then the losses are evaporation from the soil surface, transpiration, deep drainage or deep percolation beyond the root zone, and then runoff from the surface. And I want to maximize transpiration because that gives me the dry matter production, but then I want to try and minimize all the others. So I need to know what's happening in my system. Am I losing water out the bottom? Am I irrigating too much at any time that I get runoff from the surface? And also what kind of evaporation do I have from the surface, which we'll speak about later as well. But this is what I'm trying to manage as a grower. So what causes different rates of orchard evapotranspiration? This is just a little figure that tries to summarize it for you. And this will be in that guide that Lisa was alluding to earlier. And basically, there's a whole lot of factors in the soil, plant, atmosphere continuum that will determine the rate of water loss from the orchard. And then there's a number of things that you as a manager, as a grower do that also changes the rate of orchard evapotranspiration. So in terms of what's happening in the soil, how much water can my soil actually hold? What is the water holding capacity of that soil? Do I have a mulch on that soil surface? So if I have a mulch, I can reduce evaporation. How deep is my soil? Is it ridged? And that will all determine how much water I can actually hold, which becomes also really, really important when I'm designing my irrigation system and when I'm considering what is effective rainfall. Then there's also the fact that soil can be shaded by the canopy. So the canopy size impacts how much of that soil is shaded. And generally evaporation is so much lower from shaded areas than from exposed areas. And we all know that. That's quite logical for everybody. And then if we go to canopy, the canopy size will impact how much leaf area I have. So what is the potential loss of water from that orchard? The greater the canopy cover, the canopy size, generally the higher the transpiration losses from that orchard. But also the greater the canopy size, the more shading I have on that soil surface to prevent, to slow down evaporation. Things like root health are also very important. If my root health is compromised in any way, that's going to impact my transpiration rates, my ability to keep stomata open, and therefore photosynthesis. And then the atmosphere. So the atmospheric evaporative demand. So how hot and dry there is and how much energy there is in the system will determine the potential demand of that atmosphere. And that atmosphere is sucking water out of the plant. What's also really important is that the plant is not this pipe that goes from the soil to the atmosphere. It consists of xylem, and there's a number of control points along that way and a number of points of resistance within that pathway. And the tree has the ability to try and regulate the rate of water loss. And in macadamias, that is really, really important. So the rate at which water is lost from the tree should not exceed the rate at which the tree can supply water to the leaves. If there's an imbalance in that system, that's when the tree starts to wilt and suffer severe water stress and the consequences thereof, such as wilting. And so stomata start to close to regulate to balance that supply with loss. And that can be quite clearly seen in macadamias. And so at the top you see there that if it's hot and dry, it doesn't mean more and more transpiration. And so if we have a look right on the left of the graph, there's a little arrow that increases. And you can see as reference evapotranspiration, which is what we determine from weather data, and is really a nice indication of atmospheric evaporative demand. As it increases, there's an increase in transpiration initially. This is for two different size canopies that we've measured just outside Nelspruit in the Skagen Valley. And the little numbers behind just indicate canopy cover. But you can see there's a maximum transpiration rate that is achieved by both orchards. And it doesn't, no matter how hot and dry it gets, that maximum rate isn't really exceeded. And that's really an indication of stomata starting to close to control water loss, to ensure basically that the tree doesn't dry out. The other really important water loss from the orchard is soil evaporation. And this is controlled by the factors affecting soil evaporation include the area of soil wet by irrigation. So if you consider drip versus micro, as in the figures that are there, that percentage of, or the fraction of soil that's wet differs a lot. Drip, a lot of the time, that area falls within the canopy or the shaded area of the trees. Micro sprinklers, depending on what you're using, a lot of it can be exposed to quite a lot of radiation, and generally a little bit higher evaporation occurs from those systems. And as I said, it's also about how much of that wetted area is actually exposed to radiation or solar radiation. You can see in the bottom right-hand corner the radiation dynamics on the floor of a macadamia orchard. That changes over the day, and any wetted area from irrigations that's exposed to radiation is likely to have much higher evaporation rates. Also the frequency of the soil wetting, so how often do you irrigate? So drip almost every single day. Micro sprinklers, there might be a number of days between applications. And as you're getting to the end of that irrigation cycle, evaporation rates are likely to be much lower because water becomes limiting at the soil surface. So what is the crop coefficient model? So how do we decide how much water that the orchard is using? How can we have like this predictive capability that I can say, okay, well, if weather is X and Y for the week and I have a canopy that's certain size, how much water do I expect that orchard to use? And so it's a pretty simple approach, but it is fairly robust and it's widely used. And it's a really good way to have a starting point to say, okay, this is how much irrigation I need to apply for the next couple of days. So generally it uses weather data. So there's a number of weather stations around South Africa. You can get access to data. And Elsha Jaber tells me that the Mac Shield, I might have the name wrong, but that has a huge amount of weather data in, which is a really valuable platform for you guys. There's also services like openmeteo.com that provides ET0 estimates for a number of different regions. So it's a forecast, not 100% accurate, of course, but we're finding for about 4 days, it's fairly accurate. So then I get an estimate of what weather is like. So what is that atmospheric evaporative demand? Then I have a crop coefficient, or KC, which really accounts for the characteristics of that particular crop. And we can adjust that for canopy size and irrigation system. And we do that by splitting that crop coefficient into two. So we calculate something for the canopy, which is the KT, and we calculate something for the evaporation. So KT does transpiration, KE does evaporation. We sum them together, and then we can get some idea of what crop evapotranspiration is by timesing ET0 by KC. It's a very simple mathematical equation, but it gives you a lot of information. And then I can work out how much water my crop is using and therefore what I need to irrigate. So if we're looking at determining an orchard-specific K2 values, at the moment what is required? Well, it's just effective fractional cover, and that's the width of the shadow cast by the trees at solar noon. And we call that FCF, which is basically effective fractional cover. And I can measure that with a tape measure quite easily. Then the second thing is the height of the trees. So it accounts for how much leaf area I actually have there. And that once again can be done fairly easily with the tape measure. Some of my students use cell phone applications to get an idea of height. And we use that to calculate a vegetation density coefficient, which is actually, it's quite a simple equation that's written there, but it just takes into account the height, the fractional cover, and then you can see something called an ML factor, which just, we use 1.5, and it just accounts for the density of that canopy. So the more dense it is, the more leaves there are, and therefore likely the greater amount of transpiration that's happening. What we also then need, and what we've calculated from previous projects, is a KT full. And that is basically the maximum value that you would get for a macadamia orchard. And we scale that down using the density coefficient to get an orchard specific value. So we know what the maximum is, and then based on the measurements of canopy cover and height, we're able to derive an orchard specific value. And it's once again a fairly simple equation to get that KT value. What you can also see here is that in December, January, February, there's a slight decline in that KT full. And that is trying to take into account the fact that if ET0 increases, transpiration doesn't increase at the same rate. So you artificially reduce that value to make sure that you get a good estimate of water use as it gets so much hotter and drier and vapor pressure deficit starts increasing. So the last thing that needs to be determined for our modeling approach is an evaporation coefficient. We are still working a lot on trying to get really good estimates for different orchards. It's very orchard specific, and it really is quite a difficult measure to do and a difficult thing to get right, because things are constantly changing underneath an orchard, and if you have localized irrigation, it makes it very difficult. But this is just an example from our irrigation trial in Barberton, where we used another model to generate evaporation crop coefficients. And you can see from about day 120 to day 257, that is the winter period when there's no rain, the blue bars are rainfall. You can see how constant that KE becomes. And that is the evaporation that we're really interested in. That's evaporation from the irrigation system. We're not really interested in evaporation from the rainfall, because that's not ever what we want to replace in terms of irrigation. We're really worried about what's evaporated from our irrigation water. And so we can use potentially those values to try and get a better estimate of what evaporation is like from orchards of different sizes. And so now we've covered more or less how to estimate water use, what factors are driving water use. What data do you actually need for good irrigation decisions? So pose a number of questions, and I'm going to try and demonstrate to you how some of the information that we're generating and the models we have can help you answer these 4 questions. So what area can I plant with my available water? And for that, I need to know how much water on a yearly basis my orchard actually needs. And then I need to make day-to-day decisions. So how much water should my irrigation system be able to supply? Because I need to design it such that if it's a very hot and dry day, it's able to meet that maximum demand. And then how much should I apply on a day that's slightly cooler, a day that's slightly hotter, for a smaller orchard, for a bigger orchard? And so I'm going to try and show you how you can start using a simple model to try and schedule. And then what Sedileka is going to cover just now is what do I do when my water allocation is reduced? So how do I know when I can make savings, and what savings are potentially possible in a macadamia orchard? And so what I did is I took crop coefficients, and I calculated crop coefficients for an orchard with a 70% canopy cover, 7 meters in height, and north-south orientation. And I calculated what water use would be for 10 seasons from ET0 data. So I had a daily value that I then summed over a season for 5 major locations in South Africa. So I had a look at the SAMAC map, and I decided on 5 important locations and used weather data for 10 years. And so the black bar is reference evapotranspiration, so an indication of how hot and dry a certain location is. The green bar is evapotranspiration from a drip irrigated orchard. Yellow bar, evapotranspiration from a microsprinkler irrigated orchard. So all of them will be irrigated with the same theoretical system. And then transpiration values for the different parts of the country. didn't vary that much at all. I was quite surprised. Even from year to year, there wasn't that much variation. This, importantly, is water use of the orchard. So it's not considering rain, it's just considering irrigation from the system. So this represents that maximum limit of water use. If you want to then work out what your irrigation water requirement is, you would need to take into account rainfall for a particular location and what effective rainfall is. So what rain falls that will be effective for my crop that I can use, and that will give you a better indication of your irrigation water requirement. But at least we have a good starting point for different parts of the country. So I took those same locations and then I looked at the full 50-year data set that we have from each location and looked at rainfall variation in those 50 years. And as is pretty much common for all places in South Africa, the variation was quite significant. So the numbers for each bar represent the median or the average amount of rainfall over those 50 years. And then the lines either side of the box indicate how much variation there actually is. And so the variation is quite significant over every single year. If I just plotted for Nelspruit the 50 years of rainfall, you can see the up and down trend, which is quite significant, and it varied from 600 to 1,550 mils over that 50-year period. So how do you know what value to use when you're trying to calculate irrigation water requirements? So it is quite tricky. Depends when that rainfall is actually falling during a year, and it also depends, like if I have a month where I have 200 mils, but it fell within 2 days, very little of that's going to be effective, as opposed to if I have 10 mils over 20 days, much more effective rainfall. So just to show you the difficulty in trying to predict what effective rainfall is likely to be. In terms of how much water should my irrigation system deliver, I've had a look at measured transpiration data and maximum rates. So the maximum we've measured, and then average transpiration in summer, that's the top table. So really about 60 liters per day, or 1.9 millimeters per day on a 4x8 meter planting. That is the maximum we've measured. Average for that particular area was about 50 liters per day. And then if I just had a look at that model transpiration from that previous data I've just showed you, varied around about 50, 60 liters per day. So that's the maximum amount that your system probably needs to deliver in order to meet peak water requirements. If per day per tree, it probably over-designed. If you have something that can deliver 40 liters per day, it's probably a little bit under-designed. And over-design and under-design both have consequences in terms of money and in terms of stress that might occur in your orchard. So the other thing that's really important when designing an irrigation system that I just want to run through quickly is understanding the soil water holding capacity of your orchard. It's also really important when it comes to effective rainfall. So the upper limit of soil water content is known as field capacity. It's also known as the drained upper limit. So it's basically once the soil is saturated, it drains under gravity. And once it's finished draining, that is the value for field capacity. There's another point where a plant can no longer extract water from that soil because it's held too tightly to the soil particles, and that is known as capacity. And permanent wilting point will be a point where that's the allowable depletion for your plant, and that's when plant stress will become a problem, where that plant stress will start impacting your dry matter production, and that is very much dependent on your soil type and the crop that you are busy growing. And so this is just illustrates the difference in the volumetric water contents for different types of soil. So you cannot irrigate different soil textures using the same thresholds for field capacity and allowable depletion. They will change depending on the texture of the soil. So you can see that for a clay soil, a lot of water is held within that soil, but not all of it is available. Only about half of it is available to the plant because it's held so tightly to those small particles. On the other hand, a sandy soil has very low water holding capacity, but still a lot of it can be available. And so you need to adjust your scheduling according to what kind of soil texture you have. And this can also vary quite a lot over fairly short distances. If you really want to schedule well and understand the difference between soils, then look, using a matrix potential, something like a tensiometer, is much more consistent between different soil types. So this is just also a table that gives you some idea of total water available in a 70 centimeter rooting depth, depending on texture. And so that's how much total water is available, how much you can totally store in that root system, which is also really important when working out depletions. So if I'm going to schedule according to a depletion, I need to know this. And I can also use this to decide how much effective rainfall I've had. So if I have just irrigated, I know that I have got this much water, this much room available in my soil profile to store water, and I can take that into account before I turn on the irrigation again. So just to provide some information about effective precipitation, it's not easy to calculate at all, but it's very, very important to understand what is effective and make the most of it. If you're able to make the most of effective precipitation or rainfall, you're able to reduce the amount you irrigate. It not only saves pumping costs and money, but it also means it can perhaps extend your water further into the season if you ever run dry. So it's the proportion of total rainfall that infiltrates into the soil and can be stored in the soil for the crop to use. So it will exclude losses from evaporation, runoff, and deep drainage. And so it's really important to understand how the textures of your soil changes over the entire orchard and how much you're able to store if you're going to estimate effective rainfall properly and then delay irrigation until that water has been used by the crop. So if we move on now as to when and how much water should I apply to my orchard, I've tried to make a fairly simple sum just to explain to you how I convert a crop coefficient into a runtime for my pump. And so if we use the equation at the top, we first need to estimate the KC for a specific orchard. So we need to take into account, we need to calculate a KT first. And so that my situation is a 5 meter wide tree, so that's the shade underneath the trees, a height of 7.6 meters in September, and it's on an 8x4 meter planting. So then if I try and work out the effective canopy cover, it's basically the width divided by the total area or the distance between the trees. So the width of the canopy divided by the distance between the trees, and basically just over 60% of my soil surface is covered by macadamia leaves. If I then use that equation I showed you earlier for calculating the density, that works out the density coefficient is about 0.945. So that's the height times by that 0.63. I can then calculate what my KT would be for using the value for KT full from September, which is 0.35. So the KD of 0.945 times 0.35 is equivalent to 0.33. So I'm saying that my transpiration crop coefficient for that particular orchard in that month is 0.33. If I look at that graph I showed you earlier for evaporation, the KE during winter is about 0.2. And so my total crop coefficient is therefore 0.33 plus 0.2 is 0.53. Okay, so if I then times that KC by ET0, and for its data from this year, from 1 to 4 September was 20.8 millimeters. If I times that by the crop coefficient, I get 11.02 millimeters for 4 days, which is approximately 2.8 millimeters per day that I'm losing from that orchard. If I have an drip irrigation system of 0.7 liters per hour, and I have 2 drip lines per tree row, and 6 drippers per tree, my delivery rate is approximately 1.7 cubic meters per hectare per hour, or 0.18 millimeters per hour. So if I need to irrigate 2.8 millimeters per day with a run with a capacity of 0.18 millimeters per hour, I need to irrigate for 15 hours to get that amount of water into my soil for my trees. And so this might look fairly complicated, but all this can be done by a number of apps, computer programs, and there are many good irrigation scheduling tools out there. You just need the right crop coefficients for your orchard, and you can then pull in weather data from different APIs, and then you can get a good estimate of what your water use is going to be like. The only proviso is that you don't use long forecasts. We've found that anything up to 5-6 days is just not accurate enough. It's in South Africa, you just can't get more accurate than 4 days, but it provides reasonable estimates over those time. So this can all be automated to really give you good estimates of crop evapotranspiration. So how accurate is this approach? Well, we're testing this approach in Barberton, and so we're measuring transpiration from the trees. So measured KT, so that's the blue line. So that's the transpiration that we measure, and that's an average for every 2 weeks over the ET0 for that 2-week period. And then the red line is what we have estimated using canopy cover and height of the trees. And you can see it's not too bad. We're generally overestimating by about 17%. But there are times, specifically in late autumn, early winter, when the lines do meet, and that's shown by the arrows. And at that point, we seem to have some issues with a bit of stress developing in the orchard. So even though we are generally overestimating transpiration, we are getting some stress. And so we quantify that stress using pre-dawn leaf water potentials, and Seluleko will show you more pre-dawn water potentials later. It reflects the water potential of the leaves at a time when the plant water status is closest to equilibrium with the soil water potential. So if my soil is drying out and I measure leaf water potential at dawn, that leaf water potential starts to decline, become more negative as the soil dries out. It's a really nice measurement because it integrates the whole root system. It's not just a point measurement like with the tensiometer. I'm able to integrate the whole root system and see how that root system is experiencing soil water content. And so that's why we use pre-dawn leaf water potentials. And so what you can see here is where those nice circles are. You can see that's from about July to October. They are starting to decline, and so there's a slight water stress developing. Seluleko will explain a little bit more, but the stress threshold we have is minus 0.7 megapascals. If it drops below that, we have an impact on yield and quality. But the reason why we think it's declining a bit in early winter is that rain no longer is occurring, and we're probably underestimating the evaporative component of the orchard. So we're busy working on trying to find a more robust method for estimating evaporation. The last bars you can see right next to the July to October, that's a 60% ETC treatment. So we only give 60% of the control of the 0.7 liters per hour. And at that time, we were able to get significant stress, which also shows us that we are probably irrigating not too badly. If we do remove any water, we cause a lot of stress. And so it just shows that we're not horribly over-irrigating. It's just another check for us. This last year, the last couple of bars, blue, orange, and gray, stress was developing, but not as bad as the previous season. But yeah, we still got much more data to have a look at. So the last thing is, how can I check my scheduling retrospectively? How can I say, okay, well, I'm doing well or I'm not doing well? The first thing that lots of guys are doing and doing really, really well is using capacitance probes. So checking, where does my water go in the soil? Am I seeing extraction at different depths, and when should I schedule an irrigation? So this would be really good to have a look at and say, is my soil drying out? Is it not drying out with the crop coefficient that I'm using, for example? So here you can just see this is from Barberton. There's rainfall around about the 29th of September, and a massive increase in soil water content. Irrigation was stopped for a while, and then you can see the depletion, these little steps as it goes down, shows root extraction from the profile all the way down to about 80 centimeters. So that's really, really important. It's a point measurement, so you're not always sure if everything's working well. So that's where boots in the field is critical. Profile holes and augering at different depths around the orchard is very key to making sure that you have uniformity and performance of your irrigation system. Profile holes help you really understand where my roots actually are, where should I be irrigating to. You can also tell that a bit from a probe to show where that water uptake is taking place from. But I really need to have a look and see how dry my soil is lower down or how wet it is lower down. And that's not something you can't always see from a capacitance probe. Because if the rate of water that goes to a specific depth equals the rate that it moves past it, it will show a constant soil water content. So that's why even digging profile holes are really, really important. And then the last thing is water meters for all blocks, making sure that you know how much water is applied to a specific block for a specific season. And I'll explain later as well, that's really important for picking up any kinds of leaks you have in your system as well. Okay, so this moves on to Seluleka's section, who will speak about now, well, what happens if you don't have enough water? We've just spoken about the scenarios where I will have enough, but what happens if I don't have enough?
Hi everyone, I was just testing the mouse. So now this section focuses on what happens when my water allocations are reduced. So Dr. Taylor has already explained quite a lot in terms of the challenges that we, or rather the pressures or the result of a decline in water. So this is therefore going to threaten the macadamia industry's expansion, since we all know that fruit trees consume substantial amount of water to maximize yield. It therefore gives us a challenge and a need for us to investigate ways as to try and utilize the little available water to try and sustain production. These include, for example, trying to investigate what happens when you stress at different phenological stages, and also how much stress can I get away with without impacting yield and quality. So answers from this will help us save some water where possible to try and sustain the industry under such conditions. So to answer these questions, we conducted a trial in Dundrock Farm close to Barberton on Beaumont cultivar. These trees are 8 years old and are planted on ridges. So this orchard is basically on a slight slope of less than 5%, and the soil texture is a sandy loam with 30% gravel. The soil water holding capacity for the soil is 70 millimeters per meter, and considering a rooting depth of 0.7 meters, the total available water that the soil can hold is 45 mils. So what we did to answer the first question was we implemented stress at different phenological stages, which were the flower initiation or post-harvest stage, flowering and nut set, rapid nut sizing and premature nut drop, shell hardening, as well as oil accumulation. So these phenological stages then served as our treatments, and we had additional treatments like the well-watered control, which was the typical scheduling practiced on the farm. So we compared these to 40% deficit irrigation, which was considered a constant stress throughout the season. So these treatments were laid on a randomized block design and they were replicated 4 times. So it is important to highlight that each irrigation for each treatment was controlled separately, meaning that we were able to turn irrigation on and off for each stage without impacting the other stages. So to implement stress, the irrigation for that particular stage was turned off, and the trees on the same row that belonged to that phenological stage were covered with the plastic to try and exclude rainfall. In addition to that, we also wrapped the plastic on the base of the tree stems, forming a plastic skirt to try and eliminate stem flow. So this was basically a suggestion from our macadamia industry experts. So then how does water stress impact yield and quality? So what we observed here was that withholding irrigation at different phenological stages had different responses to yield and quality. So we observed a significant decline in yield as a result of stressing during the flowering and nut stage, and as well as the nut sizing stage. However, the other stages did not really differ from the well-watered control. So in terms of our quality, we also observed a production of much bigger nuts as a result of stressing during the flowering and nut stage. This probably resulted from the fewer nuts that were remaining on the tree. These bigger nuts that were produced do not really compensate for the great reduction in yield during this particular stage. And again, what we observed was that the greater distribution of smaller sized nuts was observed during the nut sizing and premature nut drop stage. So otherwise, the other stages did not really differ in terms of quality compared to the well-watered control. So for the second season, maybe to bring to attention again, for the first season, we started a bit late, of which we missed the first part of the season, which is the flower initiation stage. That is why I did not include the yield from that stage. So again here, we observed more or less the same trend, whereby a significant decline in yield harvested or obtained from flowering and nut stage, as well as nut sizing stages. Flower initiation, as well as irrigating 40% deficit, resulted in a significant decline in yield compared to the well-watered control. But in terms of our quality, again, we observed a much bigger sized nuts from the flowering and nut stage and a greater percentage of smaller sized nuts. But for the other treatments, flower initiation and 40% deficit, we did not really see any differences in terms of quality compared to the well-watered control. So then, to answer our second question, when do the trees start to experience some stress? So in order to be able to manage water under drought, it is very important to define water stress thresholds and then to constantly monitor the developing stress in the field. So to define these thresholds for macadamias, we employed the piecewise linear regression model, which is a model that is used to which is a tool that is used to model changes in the slope of straight lines. We used to model changes in slope of straight lines. So as we all know that stomatal conductance is amongst the first physiological processes to respond to water deficit, its closure directly impacts photosynthesis, as Dr. Taylor has already elaborated on that. That therefore results in a great reduction in yield. Therefore, to define the threshold for stomatal conductance, we plotted the relationship between the photosynthesis and stomatal conductance, and what we observed here was a curvilinear relationship or a segmented linear graph producing three different segments with different slopes across the stomatal conductance values that we examined. So these values were then categorized into three different zones. Zone 1 representing the absence of stress, zone 2 indicating the onset to a slight stress, and zone 3 indicating the development from slight stress, moderate stress to severe water stress. However, the idea was we then wanted to convert the stomatal conductance to a measurable value like pre-dawn leaf water potentials, which is more, or rather which can easily be adopted by farmers to use in the field. To establish this, we again employed the same model whereby we explored the relationship between stomatal conductance and pre-dawn leaf water potentials, and a significant change in the slope of the lines denoted the threshold point, and this point was at minus 0.7 megapascals. So this point is really important to define, as it gives us an idea as to when do the trees start to experience some stress, and in cases whereby you want to induce some slight stress in the field. However, the success of inducing slight stress in the field requires one to constantly monitor stress levels within the acceptable limits. So one of the tools that we used was monitoring stress through the predawn leaf water potentials. So what we observed here was that a drop beyond the threshold value that we have determined to be at minus 0.7 resulted in a decline in yield, as I've already demonstrated on the previous yield graphs. What we observed again was that the trees did not really enjoy the same amount of stress as at the different phenological stages. Like, for instance, during the flower initiation stage, where rainfall was not available and the conditions were dry, the stress was severe, and that is not what we really want to do. So therefore it is important to try and keep this threshold above or just close to it for a slight mild stress. But for some stages occurring during the rainy part of the season, we did not really observe some stress, like for instance during the shell hardening and oil accumulation stages. So these numbers that we see on the bottom of the graph, they're just irrigation figures during each of the phenological stages. Again, another tool that could possibly assist in ensuring that stress is kept within limits are dendrometers. So dendrometers basically measure fine changes in stem diameter variation. So basically the change, the difference between the minimum and the daily minimum and the daily maximum is referred to as the maximum daily stem shrinkage. So what we observe here is that a huge daily stem variation on the stress treatment was observed as compared to the well-watered control. So basically, as a result of stress, the trees tend to decline in growth as the plant water status declines. So we also try to establish the relationship between the maximum daily stem shrinkage in changes in the maximum daily, in changes with the soil metric water potential or drying soil. So we got a fairly good relationship between the two variables, whereby as the soil was getting drier, so does an increase in stress. So this is basically a good thing, because dendrometers are a continuous measure and can automatically log data. So how can we develop a stress threshold to trigger irrigation using dendrometers? So basically these are referred to as the reference baselines. So they are basically established from well-watered conditions. That is why we used our well-watered control. So again, we had two well-watered controls in the orchard, or rather in our trial. So that is why we're having two colored graphs. So considering the fact that the water requirement for macadamias is not the same throughout the season, we therefore categorized this into two parts, having the winter reference baseline is 0.025 and 0.066 for summer. So these values simply means that if your stem shrink to this amount, it means you can turn on your irrigation. However, we should also know that there are quite a number of factors influencing stem shrinkage other than the soil available water that we need to really consider. These include environmental factors such as vapor pressure deficit. That is why we observing huge spikes in our data. So all these tools, or rather all these methods that we've been using, such as dendrometers, tensometers, soil water probes, are point measurements, and in most cases, they do not really represent the whole orchard. So the use of spatial tools to monitor stress come in handy, especially in orchard with steep slope and varying soil types. These represent the whole orchard and can help manage water as well as detect diseases. So it includes the use of thermal images, which is capturing thermal images using drones. So this figure simply shows a automosaic of the orchard. So before we flew, we made sure that the trees are experiencing some stress that is passing the minus 0.7 megapascals water stress threshold. So after flying, we stitched the images to come up with this automosaic, and we observed darker tree canopies from the water stress treatment. So we therefore extracted these canopy temperatures, and we observed significantly higher temperatures on the canopies of the water stress treatment. This therefore presents thermal images to estimate water stress in macadamia orchards, which is a great win for farmers in terms of water monitoring in the orchard. However, as everything comes with a disadvantage, this data can be quite complex, and analyzing or rather processing this data is not as easy. So how can we then manage irrigation? Under drought? Irrigation is non-negotiable for many macadamia orchards in South Africa, and for maximum yield, we need to irrigate. So it is important then to identify measurable values of stress thresholds and sensitive stages for developing meaningful irrigation scheduling strategies. So if we were to consider this, it is then important to also try and manage or monitor stress throughout that particular period through the measurement of pre-dawn leaf water potentials, dendrometers, and remote sensing tools. So we have identified critical stages to be the flowering and nut stage, nut sizing stage, as well as the flower initiation stage. But if you are having a deficit irrigation treatment, it is really, really important to carefully consider it during the beginning of the season, because rainfall at that time is absent, and it is the part, or rather it is the time that really determine yield. So we also have observed or rather defined a threshold, pre-dawn leaf water potential threshold value to be minus 0.7 megapascals, which should not be exceeded in the beginning of the season. There's an opportunity to implement deficit irrigation strategies, that is inducing slight or mild stress during shale hardening and oil accumulation stage. But again, it is very important to consider doing this, because we did not really experience some stress, or rather we did not manage to induce stress during these particular stages. So therefore we do not have an idea as to how these stages respond to water stress. But importantly, it is essential to make use of rainfall during the rainy season.
Well, thanks, Seleko. So just to finish off with some really basic tips for irrigation scheduling. Irrigation system maintenance is key. And this is the document that Lisa will also distribute, a really nice document about just practical steps. No fancy tools can replace an upright micro sprinkler or an unblocked dripper. And so you can have fancy dendrometers, remote sensing tools, but if the micro sprinkler is lying on its side, you're just not going to achieve the results you want to. And so regular inspection of orchards is important, and dig holes. Easier said than done, but it's really important to auger and to dig profile holes. Not every day or every month, but just make that a regular task for many people in the orchard. And you can do field tests, so don't need fancy equipment. And then don't have a set calendar for irrigation. Try and adjust it according to weather conditions and differences in canopy size between irrigation blocks. So try and schedule according to crop evapotranspiration. As I said, there are many very good packages out there that are commercially available to people to use. And there's, other options as well. Set up Excel spreadsheets, just something that allows you to get some idea of how much water your canopy or crop is actually using. And then have some other tool, measure what's happening in your soil. So water probes are also still really, really valuable, and it allows you to retrospectively see what happens. Is it what you expected? So were you trying to get irrigation down to 0.7 meters? What I haven't said is that, leaching is also really important. So you can't be 100% efficient. You're going to build up salts. So if I irrigate and I don't see, and I wanted it to go to 0.7 meters and I didn't see it on my probe, why not? And so then you can start understanding what could be the potential problems. And then, as Seleko said, make the most of available rainfall. So even though rainfall is probably going to decline, know how much rain can be stored in the soil and make good use of it. If you are struggling to get through a season with the water you have, making the most of rainfall is really important. As you can see, with Seleko said, we covered the soil with plastic. We turned off the irrigation, and there were many instances we could not achieve stress on a sandy loam soil because of the rain. So understand that in your orchard, that you can almost stop irrigating at certain times, monitor it carefully, save a lot of water. And then, as Seleko also said, measure. Know how much water you applied. Know what water is leaving your pump house. How much left my pump house? How much arrives at the field? Because if those don't all add up, a simple little mass balance, if those all don't add up, you're losing water somewhere along the line in a leak. And that is a waste, complete waste. So how much did I put on this orchard? What yield did I get from the orchard this year? Whoa, why is it so different to this orchard, this irrigation block that's over here? Those kind of things really can help you in the long run if you have measurements and retrospectively look at, is what happened what I expected to happen? Okay, and I think we've been speaking for far too long now. So yeah, I hope everyone learned something today, got something out of it. And yeah, we'll try our best to answer questions now, if that's okay, Lisa.
Perfect. Thank you so much, Nikki and Seleko. Very informative. I see we've already got one in our Q&A. So it says, would you recommend the practice to dry out your soils after harvest or after pruning? If so, for what period?
So it is probably a time when you can make small savings in terms of water. So if you look at some of the literature on flowering and some of the practices on flowering, you want your tree to undergo a period of slight rest. So it's not true dormancy, but it's a period of rest. So you synchronize flowering in spring. So it can be cold or it can be water. The issue is how much you dry out that soil. And that's where measurements become really, really important. So what Seleko has found is that if we turned off irrigation for quite a while, there's no rainfall, stress was able to develop quite quickly and to quite a degree. And that had impact in yield in the following season. So you can, but you need to be very controlled. So then it might not be that I dry out completely. It might be that I extend time between irrigation cycles and then allow a little bit of stress. But I think it needs to be carefully monitored. So after pruning, you should also consider then that how much leaf area have I actually removed when I've pruned. So that will also reduce the amount of water that your orchard needs. So another assessment of canopy size at that point. What another student of mine is doing is trying to look at canopy size in orchard using remotely sensed data. So then you can get a nice real average of what that orchard is like rather than taking just one measurement. So I think check that. And the period would really depend on what weather conditions are like. Sometimes in the low veld, winter is not really winter. It's still hot and dry. And you will lose quite a lot of water. So that period will depend on what those conditions are like, how quickly the soil is drying out. So you can do it, but do it with care and monitor carefully. That's my advice. I know different people have different advice, but be careful.
Okay, thank you. Any other questions? I'm checking the chat and the Q&A. You're also welcome to email me and I can relay the question to Dr. Taylor as well. Just to recap, this will be recorded and placed on our YouTube channel for review later. I don't see any other questions. So I think with that, Nikki, Zaleko, thank you so much. It was great.
No, it's our pleasure to be able to do this, and yeah, a great privilege. And yeah, if anyone has any questions through Lisa, would be great. I think some people know how to get hold of me as well, and we're always happy to try and help as much as we can.
Thank you. Thank you, everyone, for your time. We appreciate it.